Have you ever wondered how your early stem cells knew which cells they would graduate to become? Whether they'd be a bone cell or a muscle cell. But first, what makes a bone cell different from a muscle cell? In simplest terms, it's the proteins they produce, which are coded for by genes. But how can these cells produce different proteins if they all have the exact same DNA? Chromatin regulation. But let's ask the expert.
Hi there, I'm the chromatin regulation chef, and on today's menu, we've got DNA methylated heterochromatin and histone acetylated euchromatin. In DNA methylation, we start with our chromatin. Then we add in our spices, sprinkling in methyl groups and DNMT enzymes to speed up our cooking. When cooking, the methyl groups attach to the cytosine bases in the DNA. When it pops out, we get a tightly packed chromatin dish, much like this angel hair pasta. Pretending our fork is RNA polymerase, it's difficult to grab that single desired strand or gene. So we can't transcribe the gene, can't synthesize our protein.
But what about the genes we do want?
In histone acetylation, we still start with our chromatin, just remembering our histones. We add in our spices, but different ones, acetyl groups and HAT enzymes. When cooking, you gotta remember that your histones in DNA have opposite charges. That's why they bind. They're dating. But the acetyl group binds to the histone, neutralizing that positive charge. It's like the histone cheats with the acetyl group on the DNA. So the DNA and the histone are less attracted. When it pops out, we get loosely packed chromatin. Like fettuccine, it's relatively easy for our RNA polymerase to swoop in, start transcribing, and synthesize our protein.
And that's a wrap, or a pasta dish.